Exercise 21.12 is a naming exercise. It mixes all the different carboxylic acid derivatives together, and some of the molecules in here are, I think, representative of the rules that we've gone through. And a couple of them are more exceptions. So I'm going to make a note of which are which as we go through this. I think it's good for you to be exposed to both. I personally tend to prefer to test on the rules rather than the exceptions to the rules. But you never know what you'll find in a standardized test like the MCAT, the PCAT, or the DAT, and so I think it's worthwhile even going through the couple examples here that are more unusual in terms of the naming, that maybe are a little far afield for what you may see on our test for our class. So this first one, completely fair game. This A is a rule rather than an exception. And we would recognize this as an anhydride. You have a carbonyl connected to an oxygen, connected to another carbonyl. That's the anhydride that we've started naming. We went through in another video. So when you want to do that, you notice the anhydride and instantly you know that the last word in this name is going to be anhydride. And either of these can be thought of as the sort of leaving group. You could think of this right molecule as the leaving group and the carboxylic acid, that this is the derivative of, being the thing on the left. Or you could think of the left thing as the leaving group and the carboxylic acid that this was the derivative of sort of being on the right. And so what you want to do is to name each of those like potential carboxylic acids. Now they don't still have the H on them. That was taken away, so you're not going to use the word acid, but you'll still use that oic suffix. So for example, if this were the leaving group, if we consider that the leaving group, then this would be like the carboxylic acid. So you'd have 1, 2, 3 carbons there, so prop. Outside of the functional group, just between the carbons, you have all single bonds, so AN, and then because this could act as the carboxylic acid, you put oic, so propanoic. Similarly, if you think of the other part as the leaving group, and this is your original carboxylic acid, you'd have 1, 2, 3, so prop. Outside of the functional group, just between those carbons is all single bonds, so AN, and if it was a carboxylic acid, you'd have that oic there. So you see that both of these branches are the same. Now when both of the branches are the same, instead of putting them both there, you can just put the name once. So for example, this can be propanoic anhydride, and that would be the full name for that compound. The fact that you only have one sort of carboxylic acid just means that that's the carboxylic acid that would have been on both sides. So propanoic anhydride. You may also see the common name for this. I would never test you on common names. I'll only be giving you IUPAC names, but the common name for this would be propionic. Oops. Propionic. That's an old name for a carboxylic acid that has 3 carbons. Not something you need to know for me, but something that you may see elsewhere. So for us, propanoic anhydride is the name for that. The next one, B, is also completely fair game, the type of stuff that we did in a previous video and that could definitely be on a test. So here we notice that you have an amide, a carbon double bonded to oxygen, single bonded to an amine. So that's an amide, and the carbon that has the carbonyl on it is going to be the backbone. And the other carbon chains coming off of the nitrogen are going to be named as branches. So the backbone name, we have 1, 2, 3 carbons, so the prefix prop. Outside of the functional group, which will be represented in the suffix, we have all single bonds, so the infix is AN, and then because this is an amide, the suffix for an amide is amide. So propanamide is going to be the name for that backbone. The branches are both benzene rings. Remember that when benzene is a branch, it's named as a phenyl branch. So these are 2 phenyl branches. Not only that, but you have to say where they're attaching. They're both attaching to the nitrogen, and so you'd have N-phenyl and N-phenyl, as we discussed in that previous video on naming amides. Okay, well we have 2 branches that are the same type of branch. They're both phenyl branches, so we can combine those. And we can put the 2 locants, the N's, together, separated by commas, like you would usually do with numbers. So NN. Always between these locants and the letters goes a dash. We have to say how many branches we're smushing together with a prefix, so di. and then the type of branch we're smushing together, which is phenyl. So those two branches together are going to be named as NN-diphenyl. And all you have to do is put those branch names in front of the backbone name, and you have the full, complete name for the final molecule. So NN-diphenyl propanamide is this work of art right here. Okay, so far these two are very common rule-based names, standard things that we've gone over already. C is maybe the first of the exceptions. C requires you to know about things called dicarboxylic acids. Carboxylic acids always occur at the end of a chain, and you can imagine the smallest chains having carboxylic acids on both ends. For example, if you had a 2-carbon chain and you had a carboxylic acids on both ends, that's a unique sort of molecule. If you had a 3-carbon chain and you had carboxylic acids on both ends, that's another sort of unique molecule. If you had a 4-carbon chain, 4-carbon chain with carboxylic acids on both ends, that again is a sort of unique type of molecule. These are all something called dicarboxylic acids because they have 2 carboxylic acids on them. And these have common names. Their names were developed for historical reasons, and so the only way you'd know them is through having memorized them. As you go on, we went up to 4 here, but you can go on, and there's a nice sort of mnemonic if you want to remember it. It's oh my, such, and then the other ones are such good apple pie. So we won't be going over these in this video, just because this is already a little bit far afield for us. But oh my, such good apple pie is a way to remember the common names for these dicarboxylic acids. The smallest one, the O, it stands for oxalic acid. The next largest one, with 3 carbons, stands for malonic acid. And the next largest one, with 4 carbons, that dicarboxylic acid, stands for succinic acid. Now, believe it or not, this S in succinic acid is something you have seen before, because that S ultimately is responsible for the S in NBS, N-bromosuccinimide. You can see it here. We'll talk a little bit more about how this dicarboxylic acid is related to the structure of that radical inducer, that N-bromosuccinimide, in the same exercise just later on. But right now, you can see that this ultimately is a derivative of succinic acid. Okay. But it's not a carboxylic acid. They've replaced the H's, the acidic H's, with carbons. So they've turned the acid into an ester. Now, normally you'd have the suffix O8 for an ester. But in this common name, there is no O. It's just succin, and then you have the ic acid. Like normally in a carboxylic acid, you'd have oic acid. Well, this one doesn't have the O. So when you go to transfer this into an ester name, the name for this backbone is not succinoate, it's succinate. And actually here, let me do that in orange so you can sort of see the connection. So the backbone here is this carboxylic acid derivative, this dicarboxylic acid derivative, and that is succinate. Okay, so that is the ester backbone name. And then all you need to do is to name the other branches, the other carbon chains as branches, the ones that don't have the carbonyl. So those are 2 methyl groups, so dimethyl. And the full name for this compound is dimethyl succinate. So that's a little far afield from us. We didn't really talk about the dicarboxylic acids, but they are things that you may be expected to know, and certainly they show up in biochemistry every once in a while, so they're definitely good to know. Oxalic acid is really common. You may have even eaten it before, maybe a little bit unfortunately. Rhubarb, the plant rhubarb creates oxalic acid. It creates it to deter animals from eating it. The stems of rhubarb, which is the part that you eat, has a very low concentration of oxalic acid. It gives a little bit of a bite to the rhubarb. The leaves have a much higher concentration, and oxalic acid in higher concentrations, as the dosage goes up, first makes you hallucinate and then ultimately kills you. So it's a poison. and so it has a biological significance, as do these other dicarboxylic acids, but so much for that. D is another sort of slightly afield exception, but it is something you could see. You might remember one sort of a similar thing that we saw with aldehydes was if you had a ring with an aldehyde attached, it was named as a carbaldehyde. That was just sort of a suffix that you added on to the ring name. So like this one would have been cyclobutane. It's in a ring, so cyclo, 4 carbons, so bute, all single bonds, so AN. And the full name for that would have been cyclobutane carbaldehyde. Oops. That's something that we went over very briefly in the aldehyde chapter. Well, here you end up with a sort of similar thing. You've got this ring, and attached to it immediately you have an amide, an oxygen double bonded to a carbon, so the carbonyl, with an amine on one side. And instead of carbaldehyde, the suffix for this is carboxamide. That's if you have an amide attached immediately to a ring. So carboxamide. Okay, let me erase this other thing so we get some room. So then we just have to, so that's, the carboxamide is actually the name for this whole thing. Oops, I should say this whole thing. And then we just have to say what type of a ring we have. And this is cyclobutane. Cyclo because it goes in a ring, bute because we have 4 carbons, 1, 2, 3, 4, AN because single bonds, and E because it's a hydrocarbon. So cyclobutane carboxamide is that orange part there. We just have to worry about the branches, and those carbon chains that don't have the carbonyls, those are named as branches. So on the bottom, only 1 carbon is there, so meth, and because it's named as a branch, YL, is attached to the nitrogen, so we have to put that locant there, capital N and then a dash, so N-methyl. The other group has 2 carbons, so prefix is eth, because it's named as a branch, you have YL. That is also attached to the nitrogen, so capital N and then a dash. So we just have to put those branch names in front of the backbone name. The E comes before the M, and so you'd have N-ethyl, followed by the next branch, N-methyl, followed by the backbone name, cyclobutane carboxamide. And you just want to put dashes in between these locants and the next letter. So the full name for this one, and this is slightly afield for us, but like I said, you may see it on some standardized test, or if you go on in chemistry, that's N-ethyl N-methyl cyclobutane carboxamide. And that's a little bit of an exception. All right, this next one is very standard, definitely fair game on a test. You might recognize this as a cyanide, or a nitrile, I should say. It's a cyanide group, which as a functional group is called a nitrile. Now, one thing that might seem a little strange that you maybe made it hard to recognize at first is you don't have the triple bond drawn, whereas the nitrile is having that triple bond between a carbon and nitrogen is a nitrile. Notice, though, that only 1 bond is drawn, and there's no formal charge on the carbon, so it must have 3 other bonds all going to this nitrogen, because no hydrogens are bonded to it either. So that's a nitrile, and that's a common way of drawing a nitrile. So if you see a CN in a molecule, that's a nitrile. Here we have 1, 2, 3, 4 carbons. The prefix for 4 carbons is bute. Outside of the functional group, we have all single bonds, so the infix is AN. And because we have a nitrile here, the suffix is O-nitrile. So the name for this will be butanonitrile. Now this is the IUPAC name. I will only ever give you IUPAC names, International Union of Pure and Applied Chemistry. There are older common names. The older common name for a 4-carbon chain was butyr. So you may see butyronitrile. But like I said, I would never expect you to know that on one of our tests. Those are older naming systems which hopefully will slowly die out so that people don't have to learn duplicate names for the same thing. But just in case you see it, that's what it is. The name that we'd have to deal with is butanonitrile. That's the IUPAC name for this compound. Completely standard type of name. F, another standard type of molecule, completely fair game on a test. You'd look at this and you'd see a carbon double bonded to an oxygen, so carbonyl, with an ether on one side. That's a sign that we're dealing with an ester. An ester. And when you have an ester, you have two carbon chains. You have one that has the carbonyl, that's going to be named as the backbone, and the suffix for that is going to be O8. And then you have the one that does not have the carbonyl, so that's going to be named as a branch. And so the ending for that is going to be YL. Okay, well, the branch, we only have 3 carbons, so prop, and because it's named as a branch, YL. For the backbone, we have 1, 2, 3, 4 carbons. The prefix for 4 carbons is but. Outside of the functional group, just between the carbons, you have all single bonds, so the infix is AN. And because we have an ester, carbon double bonded to an oxygen, single bonded to an ether, the suffix is O8. We just want to put that branch name in front of the backbone name, and the overall name here is propylbutanoate. Propylbutanoate. And remember, common names in older nomenclature, like 19th century nomenclature, which people still sometimes use now, instead of butane, you might see butyr. So you might see butyrate. But again, that's not something I would give you. I encourage you to use the IUPAC names as much as possible so that slowly the older names become antiquated and drop out, and future students don't have to worry about them. I'm exposing you to them very, very quickly just in case you see them so that you're not nonplussed by them. Okay, so that's a completely fair molecule to ask you to name. G is more of an exception. So if you go back to the one we named before, we talked about succinic acid and how that was that dicarboxylic acid with 4 carbons in it. Well, look at this succinic acid and compare it with this ring. You have 1, 2, 3, 4 carbons. Well, here you have 1, 2, 3, 4 carbons. You have a carbonyl on carbon number 1, carbonyl on carbon number 1, carbonyl on carbon number 4, carbonyl on carbon number 4. And really, all you have to do is have these 2 carboxylic acid ends react with each other. A water will leave. So here I'm going to highlight in red what leaves. And they'll connect with an oxygen, this oxygen here. So this ring is a derivative of succinic acid. Succinic acid can cyclize to form this ring. Now, this ring, if you look at it from the perspective of functional groups, you would notice that it is an anhydride. You have a carbonyl with an oxygen with another carbonyl right next to it. So that's an anhydride. And the name for this is succinic anhydride. And now you can see where the S in N-bromosuccinimide comes in. This is an anhydride, but if you replace the oxygen with a nitrogen, then it's not an anhydride, it's an amide. Now it's still a derivative of succinic acid, right? Here this is an amide because you have a carbon double bonded to an oxygen, single bonded to an amine. So the name for this would be succinimide. And if you had a branch coming off of the nitrogen and it was a bromine and you wanted to say where that bromine is, well, a branch coming off the nitrogen, you say N is the locant, and then the bromine is bromo. Well, N-bromosuccinimide is the NBS that we've seen when we wanted to do radical addition, right? We'd use that in heat or light to add a molecule, to add a bromine onto the most substituted position of an alkane, N-bromosuccinimide. And the reason why it's so good at forming radicals is radicals are very unstable, but if you form a radical on this nitrogen, it's allylic to 2 pi bonds. And so it's stabilized over that many atoms, 5 different atoms. And so that helps to stabilize this, and that means that it makes it more likely for that radical to form, and for the bromine radical to form and to react with your molecule. So sort of everything's sort of coming together. You could see how this succinic acid exception can form this succinic anhydride. If you replace it so that it becomes a succinamide, and then you put a bromine on the nitrogen, you have N-bromosuccinimide, or NBS. Okay, well, here we are, going back to naming this succinic acid derivative. The succinic acid derivative that we're dealing with here is just succinic anhydride. That is the full name for this. You've named the carboxylic acid completely, that could make it, and the fact that it's an anhydride. So that's it, succinic anhydride. This next one is also kind of an exception. If you look at the functional group here, you see a carbon double bonded to oxygen with a ether on one side. So you'd recognize that as an ester. Now you have two carbon chains. One is the carbon chain that has the carbonyl, that's going to be named as the backbone, and the other is going to be a branch. Well, you should definitely be able to name the branch. There's one carbon there, so meth, and then YL because it's a branch. The other one is a little tricky because it requires you to know the name of the carboxylic acid, which you should know. You learned it in the chapter on benzene and its derivatives. You memorized a few benzene derivatives, and one of the benzene derivatives you should have memorized was benzoic acid. If you have a benzene with a carboxylic acid attached immediately to it, that is benzoic acid. Well, if you replace the hydrogen in benzoic acid with some sort of an R group, like a methyl group like we're doing here, then it's not an acid anymore. And you'd replace the suffix with whatever the suffix is for the functional group. In this case, it's an ester, so the suffix for an ester is -08. So it's benzoate. And so the full name for this compound would be, benzoate is the backbone name, and then methyl in front of it, so you'd have methyl benzoate. Okay. This last one is more of a, so that was kind of an exception. I mean, it's kind of a stretch to require you to remember benzoate and all of that, but though you really should, technically this is completely fair. You should definitely remember the structure of benzoic acid, and then maybe the stretch is just asking you to change that common name for benzoic acid into an ester, combine that with the IUPAC rules. In I is much more straightforward. It's definitely a molecule you should be able to name. You see the carbonyl, carbon double bonded to oxygen, with an ether on one side. So again, you're thinking this is an ester. How do you name an ester? You have two carbon chains. The one with the carbonyl is the backbone, irrespective of how many carbons it has. And the one without the carbonyl is a branch. So if you're naming that branch, that's a benzene ring. When benzene is a branch, it's named phenyl. And if you're naming the carbon branch, well, there are two carbons there. So F for two carbons. Outside of the functional group, you only have a single bond, so AN. And because it's an ester, the suffix is -08, just like we saw in that last example. So ethanoate. And to get the full name, you just put the branch name in front of the backbone name, and that's phenyl ethanoate. That would be the name for that ester. That's the IUPAC name. Now remember, in common names, the ethan, the old way of saying that, is acete. And really, in the old name for this, it's even a little stranger than that. It would be acetate. So ethanoate and acetate are the same. I'm only telling you acetate because you may see it. It's a common name. But the IUPAC name is ethanoate, and that's the one that I would give you complete credit. I would give you complete credit for both of these, but since you would have been trained in the IUPAC name more rigorously, I would give complete credit, obviously, for the IUPAC name. So you could either call this phenyl acetate or phenyl ethanoate. The IUPAC name is, IUPAC technically accepts both because so many people use the term acetate, but the name according to IUPAC rules is ethanoate. And that should seem really familiar. That should be an ester you could definitely name for a test, for example. So hopefully this gave you a sense of how sure you feel about recognizing these different functional groups now that you see them all mixed up. It gave you a sense of just a review of how to name some of these functional groups, and also gave you a sense of maybe areas that if you wanted to know more, you could look into them, like the common names for those dicarboxylic acids, the names for amides that are attached to rings, and the names for some common